let us start the potential energy of a dipole. So if we assume a dipole plus q and minus q is placed in a uniform electric field. Let us say the electric field is going in this direction.
Okay.
Draw it with some light pen. So this is the electric field. This is a constant electric field. Okay.
Yeah.
We want to find what would be the potential energy of this dipole. The dipole is P from negative to positive, isn't it?
Yeah.
This is the dipole moment, and this dipole is making an angle theta with the field. Let's say this is the field direction. This angle is theta. So angle between the P vector and the E vector, right? That's theta. Now, can you tell me what would be the force on this charge due to the electric field E? Q into E on this side. It will be dragged along the direction of electric field with the force plus QE, because E is what? Force divided by charge, isn't it? Force per unit charge is the electric, so force on the charge would be Q into E. Similarly, the force on this charge would be in the opposite direction as that of the E, right? Because this will be repelled. That would be this minus Q. So if you see in a nutshell, these two forces cancel out each other because they are along the same line. Like if there is this force, another force in this direction, they cancel out each other. Okay. They cancel out each other here also, right? But they are not along the same line here. Okay, one of them is here and the other one is like this. Of course they are opposite, but they are not on the same line, so that's why they form a couple.
Alright, and then it starts moving.
Yeah, so couple means they will form a rotating torque.
Yeah.
Okay, so what is torque? Torque exerted on this. See, I told you torque is the product of force, either force into the perpendicular distance, right?
Yeah.
Either force into perpendicular distance. So either force is QE, don't take the negative sign here, multiplied by the perpendicular distance. The perpendicular distance will be this one, this distance. Okay, because we have taken this force, right, into consideration. Then we will take the perpendicular distance of this force from the other charge. So from the other charge we draw a line like this, and then we draw a perpendicular 90-degree from that force. So this is the how do we find the perpendicular. All right,
Okay.
now you know this is 2a, the total length of the dipole. This would be 2a cos theta along the theta. and the perpendicular one is called as 2a sine theta. So this would be equal to this in magnitude. So this is 2a sine theta. Getting it?
Yeah.
So QE into 2a sine theta.
Yeah.
Alright. And Q into 2a is called P, isn't it? So we can call it as PE sine theta. This is torque. Now you see one thing here. This P is a vector. This E is a vector quantity.
Yeah.
And sine theta. You know, when two vectors are multiplied and there is sine theta, can we say that they are the cross product?
Yeah.
Okay, let's keep it here only. Torque is PE sine theta.
Okay.
Because we want to find the potential energy of the dipole. So let's just keep it here. Now next, what we do, if we rotate the dipole through a small angle d theta, if we rotate this dipole against, so if dipole is rotated through a small angle d theta, all right, then there would be a small amount of work done to do that. What that work would be? See, work in the linear motion is what? F dot ds, force into displacement,
Yeah.
right? But so if this is dw, then that would be ds. If it is w, then it is s. This is in linear motion. In rotational motion, the work would be, force is replaced by what? Torque. And the displacement is replaced by, see, since the displacement in the rotational motion is called the angle, okay,
Yeah.
because there is no linear, so this will be d theta. This is the analogy. This is the linear motion, this is the rotational motion. In rotational motion, theta is the displacement, okay, because we rotate using, there is no linear motion there, and the force is replaced by this torque. So the small work done in doing this thing, that rotating this small angle d theta, is torque divided multiplied by d theta. All right, and we have just found the value of torque. We can replace it with PE sine theta. So PE sine theta d theta, this is dw. All right, now we want to find the total work, okay, total work in displacing the dipole from some angle theta 1 to some another angle theta 2.
Okay.
We have found the small work dw. How do we find the whole work? I told you, using integration. You add these small works,
And then you get the.
you will find the total work. So dw is replaced by integral of PE sine theta d theta, and this will go from theta 1, because we are rotating it from theta 1 to theta 2. These are the limits, okay.
Yeah.
That is how we substitute the limits, okay.
Yeah.
So this P and E, they are already constants here. E is the electric field, which is a constant. The dipole is a constant, so you can take that out. So PE, and you have left with integral of sine theta d theta from theta 1 to theta 2, and the integral of sine theta is what? It is, so integral of sine theta is minus cos theta, all right?
Okay.
And if you are finding it with limits sine theta, so that is still minus cos theta, but you need to enclose this in bracket and substitute the limits. How do you
Okay.
substitute that? First replace theta with theta 2, so minus cos theta 2,
To the power.
not power, let's just
Oh.
replace theta with this theta 2, minus, you put a minus sign and then place the second limit, so minus cos theta 1.
Theta power. Okay. In which chapter are we gonna learn this?
It is the second part of the book. We are studying the first part, so there are 2 more chapters remaining, and after that we'll study integrals. Yeah, so PE, don't need to worry about that.
Because integrals are everywhere and I don't understand.
Yeah, why would you understand? Because I have not told you as yet.
Yeah.
It's in the second part, so because this derivation is not gonna come anyway.
Okay.
So theta 1 to theta 2, so what you will get, the answer would be PE. Should I write it directly?
Yeah.
So what you will get, PE minus cos theta, theta 2 to theta 1, and if you solve this, you will get PE cos theta 1 minus cos theta 2. Why theta 1 is before theta 2? Because this negative sign and we change that.
Yeah.
So this is the total work done in displacing this dipole from angle theta 1 to some angle theta 2.
Yeah.
Okay.
Yeah.
Now if initially the dipole is perpendicular to the electric field,
Okay.
then what will happen? This theta 1 would be 90 degree.
So that would be 0.
So theta 1 would be 90 degree, cos 90 is 0.
Yeah.
And then let's say theta 2 is some theta. So from theta
Yeah,
1 is
theta
equal to 90 degree, which is like, it would be something like this, okay?
Okay.
Plus q minus q. We are rotating it, all right? And after rotating, we are getting something like this. And this angle is now theta, okay? This angle is 90. So if theta 1 is 90 and this theta 2 is just theta, some angle, then what will happen? Work done would be minus PE cos theta, isn't it?
Yeah. Yeah.
And what is the multiplication of two vectors with a cos theta? Suppose A dot B is what? A into B into cos theta. Can we say that this is negative of P dot E? Negative sign taken out common, PE cos
Yes,
theta.
yes, yes. Yeah. Dot E. Dot product.
Yeah, so this is the final.
Yeah.
Now I already told you that the work done in bringing any two charges or any charge number of charges close together is stored as the potential energy of the system. So this W is the potential energy of the system.
Yeah. Okay.
Because that amount of energy would be required to move them to infinity again, and that amount of energy was taken by external forces to to like arrange them in this way, isn't it?
Yeah.
That energy, the work done, is stored as a potential energy. So you should remember this
Okay.
formula, that the potential energy of a dipole is P dot E minus P dot E. Okay.
Okay. Yeah.
All right. So let us do a question on it if it is there. Do example 29.
Okay.
How will you do this question? The length of dipole is 2 centimeters. All right.
Oh.
So that means 2a is given. 2a is how much? 2 centimeters. That is given to uniform electric field. E is given 10 to the power 5 Newton per coulomb. Torque is experienced 8 into 10, 8 root 3 Newton meter. Calculate first magnitude of charge on the dipole. Torque is how much? P E sine theta, right?
Yeah.
Torque is given, E is given, sine theta can be calculated.
So.
No, just P is Q into 2A. Q into E into sine theta. This is 2A. Everything is for us. Root 3 is Q into 2A is 2 divided by 100 because that's centimeter. E is
Yeah.
10 to the power 5. Sine 60 is how much? Root 3 by 2.
I mean, it's
2 cancels
yeah.
out. This would become 10 to the power 3. 3 also cancels. Q is how much? 8 divided by 1000.
Yeah.
So 8 into 10 to the power
That
minus
would be.
3 coulombs. Second
Yeah.
part is potential energy of the dipole. U
Energy.
is minus P dot E, which is P E sine theta. P is how much? Q into 2A. So Q into A is 2 by 100 into E is 10 to the power 5 sine 6 by 2. This cancels out. 10 to the power 3, 10 to the power will become 10 to the power 2 as a whole. Minus
Yeah.
3 and plus 5 is 2. That is 100.
Yeah.
This 100 will cancel out this 100. Alright?
Yeah.
So the final answer is minus 8.
So we're left with
Minus 8 only. Okay?
803.
Yeah, I'm sorry. This is cos 60, no? So cos theta. Cos theta is cos 60, which is half. So not root 3 here. Okay, now it is correct. Let us start this thing. Behavior of conductors. You already might know what are conductors and insulators. This is already in class 10th, okay? So you can just read it on your own. What are insulators, what are conductors? These are just class 10th definition, right? Free and bound charges. Or free charges are the electrons, bound charges are inside the nucleus, right?
Yeah.
This is just class 10th. I am just starting this topic. Behavior of conductors in electric field. Okay.
Yeah.
So behavior of conductors in electric field, inside the electric field. What happens when a conductor is placed inside the electric field. There are various points that we'll see. First is very important one, that the net electric field inside a conductor is zero. So let us see, let us prove it. Let us take an electric field. This is inside this. There is an electric field. So this is positive. This is negative. Inside this we are having an electric field like this, from positive to negative. So let's erase this. Let's not draw the electric field because it's there. I just told you that it's there. Okay, now inside this we are placing a conductor. When we place a conductor inside it like this, as you know, conductors have 3 electrons to move. Okay, they can easily move from one place to another. So this electric field inside, what this electric field was present already, right? This, from positive to negative. Now when it crosses the conductor, you can see I have not drawn any field inside that. Just there is no electric field, it just crosses like this. Okay, but outside the conductor it is going normally like this, right? This is the external electric field, E external, that was already present. We put the conductor in this electric field. Now we have what we have seen. We have seen that there is no field inside it, right? Why does that happen? See, when you place conductor inside electric field, okay, as I told you that conductors have free electrons, so the electrons, those are negatively charged, will get a force due to this electric field external. Those electrons would be moved in the direction opposite to the field because they are negatively charged particles. They will move opposite to E external, right? So all of the electrons will move in this direction because electric field is going here, so electron will move in the opposite direction. And hence what will happen due to this effect, that all of the positive charges will at this end. All right,
opposite charges. What?
the electrons are moved in this direction opposite to the
opposite
to the electric field. See, if there is this conductor, you know, there are positive charges and negative charges. All right, if by some means electrons are being pushed in this direction, then because you know electrons and the protons, they repel each other, positive and negative cannot be at the same point. So if they are moved in this direction, naturally the positive charge will tend to go away from it. They would be collected at the other end. The same thing is happening here. The electrons are moving here, that's why positive charge repel them and they are collected at the other end. Okay, due to this what happens is that an opposite electric field is automatically created inside the conductor. Whenever there is a positive charge and there is a negative charge, the electric field is there, that will be going from positive to negative. This automatically creates an electric field, right?
Yeah.
So there will be an electric field going from positive to negative that will be created in this conductor. Okay,
Yeah.
and this electric field is called induced electric field, which is induced due to this phenomenon. Okay,
Okay. Yeah.
so what happens that this E external and this E induced is in both are in opposite direction, so they cancel out each other, and effectively the net electric field inside the conductor is zero.
Yeah. Okay.
In fact, it was going like this only, but the E induced cancel the E external field inside the conductor, That's why the net electric field, the final scenario would be something like this only that I drawn earlier. If this is positive, this is negative, conductor will be just empty, no electric field inside, like this. Finally this thing happens because E
Yeah.
external inside that cancelled with E induced inside that, and that's why we say that electric field inside a conductor is zero. Okay,
Okay.
this is the first property. Let us talk about the second
Okay.
property. At a point just outside the conductor, electric field is perpendicular to surface conductor. For example, if this is a sphere, this is a conductor, right? So if you place it in an electric field which is like this, you know
Yeah.
so what will happen finally is that this will like something like will go simple, I am drawing like this.
Um. Is it because electric
Because
field thing?
when you put a conductor inside the field, electric field at the surface become perpendicular to the surface. This is 90 degree, this is 90 degrees, this should be 90 degrees. That means the electric field should be tangential to the sphere because that's the 90 degree to the sphere, isn't it? The 90 degree to the
Yeah.
sphere is not the tangent, sorry, the normal. Tangent
The
is
normal
this,
as well.
the normal is this. Tangent is this, the normal is this. Electric
Yeah.
field to this conductor outside the surface should be a normal. That's why
Yeah.
when you put it inside this, the electric field deviates and readjust themselves like this.
Okay.
And inside the conductor there is no electric field. I already told you this is empty.
Yeah.
So they will go like this and come out like this. But why does this happen? Let us take another example. Let us take a cylinder instead of a sphere, right?
Okay.
If you place a cylinder in the electric field which is like this, what will happen? See, this is already perpendicular. The cylinder surface is already perpendicular to the electric field. They will not deviate, rather they will go and skip this and then go like this. Now in this example we can see why this is always 90 degree. See, if this were not 90 degree, for example, if it were some angle,
Okay.
then there will be a component of the electric field. This is E, and this is some theta. If this is not 90, if this is some theta, then this would be E cos theta, and we will
Yeah.
get some component here, E sin theta, right?
Yeah.
You can also draw this if cylinder is drawn like this. I'm drawing it wrongly. This will not happen, remember, because this has to be always perpendicular. This is not 90, right? This is not 90.
Yeah.
This
Yeah,
is some theta, let's say. This is E. Now what will happen? This is E sin theta. This is E cos theta. No. Hmm. Let's do it the other way around. Let's not draw the cylinder. Let's draw it like this. Cylinder is still like this, and electric field is, it is going like this. I'm not saying it is correct. Let's assume that if it is like this, then this angle theta, so this is E cos theta,
Yes.
and this will be E sin theta.
Sin theta. Yeah.
So if this is E sin theta, then this, on the surface of this conductor, on the surface there is some electric field, right, which is in this direction from bottom to top.
Yes. Yeah.
And when there is some electric field from bottom to top, this will help in rearranging the charges that are inside the conductor. What does that mean?
Yeah.
See, this conductor has free electrons and holes, free electrons and protons. When, if there is an electric field along the surface, then what will happen? Those electrons would be dragged down to the bottom, and all the positive charge would move in the direction of electric field along the surface. I am talking of the surface only, not inside, remember. I am just drawing it. This is on the surface, you know, the curved area of this.
Yeah.
So that would happen. All the electrons would be here, all the protons would be here. But practically that does not happen. We see that it does not happen. Alright?
Yeah.
We find that this thing is not happening. All the charges are at their respective places. The charges are distributive in plus minus haphazard direction, like they generally are. Okay?
Yeah.
So from this thing we can tell that the electric field is perpendicular to the surface, like this only.
Okay.
Because we don't find it in experiments. We don't find that we have some charge at the bottom which is a negative charge and some charge, because that, in that case we can use it as a battery, you know. The positive charges are here, the negative charges are collected here. You can put in some bulb here and you can connect a bulb to it, you know, with a wire.
Cool. And then the bulb will light up.
Yeah, this does not happen in practice. All right, so I think we should continue in the next class. There are a few more points to take.